and Wang et al. So this was very interesting because back in 2022, ChatGPT came out. Then eventually Meta produced an open source system, Llama. And then there were always questions about, like, what was it that allowed ChatGPT to become so effective compared to previous versions. And this was in some sense an independent confirmation that what OpenAI had advertised was indeed the case, that I guess a key aspect was to do reinforcement learning from human feedback. So we'll discuss that in a moment. And it's really exciting to see how reinforcement learning has played a key role here. Now, if we look at this year, DeepSeek at the beginning of this year also produced a technical report. And then here's another quote. This behavior, and here they were referring to the behavior of reevaluation, is not only a testament of the model's growing reasoning abilities, but also a captivating example of how reinforcement learning can lead to unexpected and sophisticated outcomes. So this is really interesting because in the realm of machine learning, right, so machines are effectively trained to often mimic what's in the data, because we'll have a target and then you essentially do classification or regression to achieve the target. But with reinforcement learning, there is also a search component, an exploration component, and that allows agents to essentially discover new strategies, new policies that perhaps humans would not have thought about initially. And at least for DeepSeek, they did observe that by using reinforcement learning, they obtained some agent that was doing things that they had not expected, in particular the behavior of reevaluation. Okay, so now let's get into the details of how large language models are trained and where reinforcement learning plays a role. So the recipe that's been around for at least 3 years now is to start by collecting some demonstration data, and then you train with supervised learning. So the idea is that you have your large language model. It is effectively a policy, but from a supervised learning perspective, we can train it to maximize the likelihood of the data that we train it with. And then so if we simply harvest lots of text and other sources of data around the web that are public and so on, then this gives lots of examples of how a system might want to converse. And this was always the starting point. So just do supervised learning to essentially imitate what humans do when they converse. Now, the second step after that is to collect some comparison data and then train a reward model. So this is where reinforcement learning starts to play a role. I'll explain this in more details in a moment, but the idea is that you could have a prompt, and then the language model can produce several responses. And now you could ask somebody, so a labeler, to essentially rank those responses, and then the system can learn from that. And in particular, in order to generalize well to unseen cases, it's best to first train a reward model that would mimic the ranking that humans provide. And the benefit is that then this reward model can rank any pairs or any combination of responses. And once you have a reward model, then you can do reinforcement learning. And then this is the final step where you would essentially optimize the large language model, which is the policy, to really align with the preferences that the human labelers here have expressed when they provided some ranking. Okay, so now let's make this more concrete. So when, again, we're using reinforcement learning, the idea is that we have, let's say, a prompt. So we could ask ChatGPT or any other LLM, explain reinforcement learning in 3 sentences. And then when I asked ChatGPT some time ago, I got the following response. So it's actually a good response. But then I can ask it to give me a second response. And I got a second one that is clearly different, but also quite good. And then it will ask me, was this response better or worse than the previous one? So in that case, you see it's asking me to rank those two responses. And when I click on better or worse or same here, I'm essentially providing some feedback that can be used to train a reward model and eventually to improve the large language model. So now how does that work under the hood? So I've got here the key steps and the key equations, and then we're going to see in more details how that works. But first, you see you collect a preference data set. And what exactly that means is that you have a set of states with pairs of actions. And here those, well, I guess a state, this would be a prompt or otherwise a past conversation. And now the pair of actions, these would be essentially two possible responses that the system could provide. And here, the plus and the minus indicates that among those two responses, we prefer the first one. So A plus is the preferred response, and A minus is the one that is not preferred. Okay, and generally speaking, we'll use a symbol here to indicate preference. Okay, so once we have such a data set, then we can train a reward model according to the Bradley-Terry model. So the Bradley-Terry model is essentially this objective here, or this equation here. The idea is that we're training a reward model R with parameters theta, and it needs to, I guess, provide a numerical response for a state action pair indicating how good is this response for this prompt. And now here we're comparing two responses. So the idea is that we're going to ask the reward model to produce a numerical value for both. And ideally, what should happen, you see, is that for the preferred response, the reward should be higher, and then for the other one should be lower. And here you see if the difference between those two can be increased, then according to this equation, when we pass this through a sigma in, this will increase the probability that indeed someone would, like a human labeler would agree that this response is preferred. So the idea is that you see we're going to maximize the probability, or in fact here the log probability, that A plus is preferred over A minus, and this will align with the human preferences. Okay, once we have trained a reward model in this fashion, then we can use it to fine-tune the large language model by reinforcement learning. And then the main equation here for doing reinforcement learning is simply to maximize expected rewards. So this is pretty standard in reinforcement learning. I mean, that's always our objective. We're going to maximize expected rewards. And then in this case here, there's an additional term where we subtract the KL divergence between the large language model that we're trying to train, so pi phi, versus the pre-trained language model that we had before we're doing this fine-tuning step. So this is a form of regularization. It's related to the maximum entropy framework. We're not going to go into more details about this, but it has the benefit of making sure that when you fine-tune, you don't change the language model completely. So it ensures that whatever it was trained with, it would simply change a little bit. And this way, it ensures that you won't have surprises in terms of the behavior of the language model. Okay, so let me pause here. Let me see if there are any questions about these equations or anything I've talked about so far. Okay, so if there are no questions, and here I'm not sure if there's a chat window. I cannot see any chat window, so if there is, just let me know if somebody's asking a question in the chat, but otherwise I guess I'll just keep going.
Sure. I'm gonna tell you if anyone has any question in the chat or raise their hand. I'm going to.
Okay. Yeah, I won't be able to see people raising hands either. All I see is my screen. So I guess just
Sure,
tell people to speak up when
sure,
we
sure.
raise our hands here.
I manage the session with you. No problem.
Okay.
Yeah.
Great. Okay, so let's keep going. So, uh, yeah, I've explained now reinforcement learning from human feedback, but I'll go into more details about how these equations arise in a moment. But just to kind of set the stage, let me just illustrate now um, graphically how that works, and then we're going to see some improvements as well for reinforcement learning from human feedback. So I guess to summarize the equations that I just described, so we typically start with a pre-trained model. This comes from the supervised learning stage. And then, as I explained, we're going to get some preference data. Then we train a reward model. So this is this equation here with the Bradley-Terry model. So this gives us a reward model. Once we have that, then we can fine-tune the large language model. So this is done by reinforcement learning, and this is essentially this equation here. Okay, and then I'll explain in a moment as well how afterwards, once you've got your fine-tuned large language model, then you can do text generation, and then some popular approaches include nucleus sampling and top case sampling. Okay, so this is graphically how things work for reinforcement learning from human feedback. And now I should point out that this tends to be expensive because the reinforcement learning step here is not an easy one. So it does require quite a bit of compute, and it's also difficult to have proper convergence. Now, one of the benefit though is that once you have your fine-tuned large language model, then doing the text generation, in other words, executing the policy using nucleus sampling and top case sampling tends to be fairly fast. Now, there have been some improvements on this that we're going to cover in more details as well. So one improvement is known as direct preference optimization. Um, Here, if you compare the two drawings, the two diagrams, you'll notice that here we're missing the reward model. So the big thing about direct preference optimization is that we can obtain a fine-tuned LLM without going through the step of building a reward model. So we effectively save one step. And on top of that, when we do the fine-tuning, we don't use reinforcement learning, but we're going to use maximum likelihood learning. So it's going to be a form of supervised learning, which tends to be easier, especially for convergence and stability. Okay, so in the literature, you'll see that very often people use direct preference optimization to do reinforcement learning from human feedback, and this is essentially the diagram here that they're using, and I'll explain in more details how this works in a moment. Okay. Now let me point out one other improvement, which is known as reward guided text generation. So this one also saves a step, and you'll notice that the step that is missing here is fine-tuning the LLM. So this one is interesting because we start with a pre-trained LLM, we have our preference data, we construct our reward model, but then we go straight to text generation. So we never have to fine-tune the LLM. That is in fact the most expensive step. So as a result, training can be quite inexpensive compared to the other two. But the I guess the trade-off is that now when we do the text generation, it's going to be based on the pre-trained LLM and the reward model. And then so there's going to be some additional computation done with respect to that reward model at the time of text generation. So generation will be slower. So that's the trade-off. Okay, so now what I'll do is explain in more details, I guess, these three approaches, what are their pros and their cons, and yeah, I think this is pretty exciting. Okay, so coming back now to just doing alignment in general. So you see, we discussed how we collect a data set of preferences. This would include always a triple of a state, which is a prompt. Then there's a first response that we denote by A plus, a second one that's A minus, that indicates that we prefer the first one over the second one. And where this preference data would be used, this could be used to fine-tune some large language model based on instruction data. You could have various domain data, client data, fairness data, toxicity prevention data, etc. Okay, so many tasks when we want to take a pre-trained large language model and then fine-tune it for improving the performance with respect to a task, people would often leverage these types of data sets and then obtain in this way an improved large language model. Okay, so if I just go back to I guess how the reward model was trained. So this was the original reference where the idea of training a reward model from preference data was first proposed. So this goes back to 2020. Again, our reward model is simply providing a real number. And now if we have several responses that are ranked, so this is ranked by a human annotator, then we can train the reward function using, again, this Bradley-Terry model. So it's simply trying to maximize the log probability that that one response is preferred over the other one. And here the idea is that I should be, I guess, smaller than J, indicating that AI would be preferred over AJ. Okay, so that's the idea, that we're maximizing the log likelihood. Okay. Yeah, and now again, when we are fine-tuning the large language model, as I mentioned briefly before, so this would be done using this equation here. This is the reference that first proposed that. So in fact, this was first integrated into Instruct GPT. So if I remember well, this reference is about the tech report for Instruct GPT. So Instruct GPT was an early model that followed GPT-3, where they were fine-tuning the LLM to follow some instructions. And this was very interesting because up until that point, all of the training was always about simply maximizing the likelihood of the next token according to some text found on the web or in some public sources. And the challenge with that is that this is okay if you simply want to obtain a policy or a language model that converses well and is good at just producing language that's human-like, but it doesn't necessarily help in terms of answering specific queries. So here the idea was that you can improve the responses by using this reinforcement learning technique. And at the time, to optimize this, they use the PPO algorithm. And now I'll go over briefly how that works. I understand that you guys have seen this earlier in the course, but just to remind everyone, I'll go over this briefly. So when we do policy optimization, the idea is that for large language model, you can optimize a policy in a supervised fashion. Here, it would mean first that we would have pairs of states and actions, where here the star indicates that the action is optimal. So that's always the case in supervised learning. So we have to know what is the optimal action or the target, and then we can simply maximize the likelihood of the correct action. And then we would do a policy update just by following the gradient, right? Now, reinforcement learning, it differs slightly. The idea is that you see now you would have a state, an action, and a reward. So when you have triples like this, the point is that the action is not necessarily optimal, but on the other hand, you have a numerical value, the reward, that tells you how good this action is. So now you can do an optimization based on that. In the case of reinforcement learning, we would maximize expected rewards. And now what's very interesting is when you do gradient descent, a bit like you would normally do in supervised learning, then you obtain an objective where the gradient is very similar to the one for supervised learning, but it differs just by one term right here, g of n, which is simply the accumulated sum of rewards for a sequence. So the intuition here is that in reinforcement learning, because we don't know whether the action is optimal or not, but we have a score in the form of the reward, then what we really do is like, it's like saying, okay, I'm going to assume that this action, let's say, is optimal. I'm going to take a step in that action at gradient, but because I'm not actually sure that it's optimal, but I know its score, then I'm going to reweight this gradient by how good that action is based on the reward. So Gn again is a sum of the rewards. So that tells us like how good is this action, and I guess the rest of the policy afterwards, and then we reweight our gradient based on that. So that's like the simplest way to look at how policy search techniques relate to supervised learning, right? So this is really the only difference here. So now when we, I guess, use reinforcement learning like this approach that I described does correspond to what is known as the reinforced algorithm. So this is the pseudocode, but I understand that you guys have seen this already in the course, but this is just as a quick reminder how the reinforced algorithm works. Okay, so you have a loop for episodes, then you get a sequence of state, action, reward triples, and then you simply compute this sum of rewards, and then you do your gradient update with this equation, which is really the policy gradient. Now, okay, so this here is the reinforced algorithm, which is like one of the most basic technique, and it does suffer from the fact that there's a lot of variability, stochasticity in the sequences, and therefore the gradients. So we can reduce that by using a baseline and essentially improving the speed and the convergence of policy gradient methods. And one popular approach for doing this is proximal policy optimization, and it works more or less the same as reinforced, except that the objective here has been adjusted. I should say here that the way it's adjusted is a bit of a heuristic, but in any case, it is similar in spirit to the reinforced algorithm. And here this shows what the difference is. So it's really in how we update the policy that we take steps that are different, and this is the main objective here that would get optimized. And here I guess, yeah, in this approach, one key difference is how the sum of the rewards, now we're going to subtract from this the value to obtain a baseline and essentially reduce stochasticity and noise to improve convergence. Okay, so the final step after you've trained your large language model like this in reinforcement learning is to now generate text. And the way it would be done in NLP is, for instance, to consider, let's say, the approach known as nucleus sampling. So from a reinforcement learning perspective, you see the large language model is a policy. It's giving us a distribution over the next tokens. And now, I mean, if we are simply going to apply the policy, it would mean that at every step we simply sample a token from that distribution. Now, in practice, practitioners do things a little bit differently. The issue is that if you have a distribution over all possible tokens in the dictionary, well, there's going to be some good tokens and some bad tokens. And the problem is that because the policy is stochastic and it still has some probability for a lot of bad tokens, and we would not want to have mistakes or some noise in what is being said all the time, then a common trick is to consider what is known as the nucleus. So here you would pick, let's say, some amount of probability and only consider the tokens that whose probabilities add up to that amount, so that you only sample from those top tokens, and then you can ignore the unreliable tail. Okay, so as a concrete example, so like if we have the sentence, what does the yield, and now we want to produce the next token, and here for the next token we can have keyword, return function, generate statement, etc. Those have a high probability, so we are going to sample from those, and we're simply going to ignore the tail so that we reduce the likelihood of getting some really weird sequences. Okay, so this is a common approach, and it's something that is typical in NLP, but maybe not so frequent in reinforcement learning. Okay, so now let's look at some of the initial results of doing this type of reinforcement learning from human feedback. So the first results were reported for Instruct GPT. So this was a precursor to ChatGPT. And it was very interesting because at the time, people were building models that were like just getting larger and larger and larger. So at the time, OpenAI had models that could reach 175 billion. Today, who knows how big their models are, but still, 175 billion is quite large. And we can see here for different variants of GPT how well it performed on some task. Okay, so here the idea was to compare the output of some model to a base model. The base model was only trained by supervised learning. So SFT is supervised fine-tuning. So that means that you're simply training in a supervised fashion. And so the win rate here, if we have a win rate that's higher than 0.5, that means we have a better model than that. And if it's lower, then we have a worse model. So the model that they took to be the baseline was their supervised fine-tuning model that had 175 billion. So up until that point, that was their best model. So now they treated it as the baseline. So that's the 0.5 line. And now you see the two lines above are obtained by doing reinforcement learning from human feedback using the PPO algorithm. Okay, and what's really interesting is that you see here with supervised fine-tuning 175 billion, this is the level it reaches. But now with reinforcement learning, you can beat a 175 billion parameter model with a much smaller model. So here only 1.3 billion. So reinforcement learning was really effective in terms of driving the performance, and this did not need a huge model. Now, obviously, you can still consider a large model. So now if you go back to 175 billion, then the performance improves even more. But essentially, this is, so Instruct GPT was a model that was never released publicly, but it was the basis of ChatGPT. And in some sense, the amazing performance that blew everyone's mind when ChatGPT came out was rooted in this type of improvement here. Okay, so let me stop here and see if there are any questions about what I described using reinforcement learning from human feedback. Okay, so if there are no questions, let's continue. All right, so now I want to go back to this picture. What I described so far was essentially this diagram here. Now I'm going to talk about the second diagram. So an improvement that was done in 2023 by Rafaelov et al., and it's known as direct preference optimization. And again, the key here was to simplify the overall process by avoiding to compute the reward model. Okay, so direct preference optimization works as follows. So um, you simply collect your preference data, and then you directly fine-tune the language model by maximum likelihood. In contrast, you see what we just discussed. You would first create a reward model, and then after that, use it to fine-tune by reinforcement learning, which is itself more complex and more difficult to train than just maximum likelihood. Okay, so how do we manage to bypass reinforcement learning? And in fact, I should point out that this approach of direct preference optimization is not an approximation. It is mathematically equivalent to doing reinforcement learning from human feedback, where you first build the reward model, and then after that, you do your reinforcement learning. So this was quite shocking for a lot of people that you could obtain a supervised learning technique that is simpler and yet mathematically equivalent. So we're going to see in a moment how that works. Okay, so the key for bypassing reinforcement learning and in fact the reward model is to look again at the objective. So the reinforcement learning objective was this one. So you maximize expected reward subject to a KL divergence regularization term. And now it turns out that this optimization problem, you can show that it has a closed form solution. And this is what the optimal policy will look like. I'll show you the derivation in a moment, but this turns out to be a really important observation. In fact, this is quite rare because in reinforcement learning, usually, we have our reinforcement learning problem, and then finding the policy, this is where you have to use an algorithm like PPO or Q-learning or whatever, which is an iterative algorithm that will take time and then, will gradually approximate the optimal policy. And I mean, it never really converges precisely to the optimal policy, right? So now what's really interesting is that for this particular mathematical objective, there is a closed form solution. So we actually know that the optimal policy will look like this. So it will be essentially the original policy multiplied by an exponential of the reward. Okay, so this is interesting. So here, what this means is that the original policy is like a distribution over the possible next tokens. And now, if you're going to do fine-tuning with reinforcement learning, and that it's the rewards that are driving everything, what this equation says is that now you're going to rescale those probabilities after you multiply them by the exponential of the reward. So in other words, you see tokens that would normally yield higher rewards, we're going to increase their probability, and those that yield lower rewards, when you multiply like this, it will lower their probability. So that makes sense intuitively, but it's not just an intuition or an approximation here. This is the mathematical solution, or at least the form of the optimal policy for this optimization problem. Okay, so I'll show you in a moment how we derive that, but once we have this equation, then we can manipulate it to isolate the reward. So I'm just going to isolate R here and move everything on the other side. So it gives us this expression. So the log of the optimized policy divided by the reference policy plus log of ZS. ZS was our normalization constant. And once you have this equation, then you can go back and then just plug it into the objective for training the reward model. So if you remember, the reward model was trained based on the Bradley-Terry model. So it was this equation here that we used. Now, if I simply replace R by this expression, then I get the following version for the loss function. And now you see what we've effectively done is like, we never have to do reinforcement learning. Like we get the um, closed form solution, plug it in here. And now this objective was really a supervised learning objective because this was the objective for training the reward model. Now we want to bypass the reward model. We would like to directly optimize the policy. And that's why when we replace the reward model by this expression that comes from here isolating the reward model, then it gives us a way to directly optimize the policy. So this is the beauty, and this is the core of this approach, direct preference optimization. So now we're simply going to use this objective to directly optimize policies, no reinforcement learning, and it's really just supervised learning. But I mean, we're still optimizing the parameters of the policy, just not by reinforcement learning as usual. Okay, so maybe the main thing again that I still need to explain is really how do we get this as an optimal solution or as a closed form solution. So here's I've got the derivation. Okay, so it's not that hard. Um, I'll I guess I'll make the slides available after this. For the purpose of this talk, I'm not going to go into the details of every step, but there's nothing difficult, right? Like each step is either some definition or I'm going to rewrite max as minus min, etc. So I've got here the justification for every step, so you can follow that. And then the beauty is that we arrive at the end um, to the optimal policy. So that's a confirmation that this approach works when we have an optimal policy of this form. Okay, so now when we look at empirical results, um, so Rafael et al. Produced those results. Here, they're looking at the amount of reward and also how much a policy has changed with respect to the initial pre-trained policy. We can see that their approach, direct preference optimization, really works well in terms of maximizing rewards. And this is perhaps just measures of rewards, but you could ask like, are the resulting policies indeed good in practice? So they also have this plot here that shows that the win rate is essentially how often somebody would prefer um, the response produced by one model versus another model. And then so here their model is DPO, so you can see that it tends to be preferred over the other techniques. So it is producing high quality responses. Okay, so that shows that it works really well. Now in theory, there is no reason why DPO should be better than PPO if you just do classic reinforcement learning from human feedback with PPO and then you train forever. Okay, so you train um, as much as needed to get convergence to really an optimal policy. The difference is that DPO never has to train to obtain the optimal policy. It simply utilizes the fact that there's a closed form solution that gets plugged in directly, and then you do supervised learning. Now, in the same way, if you do supervised learning forever here until you really have like the best possible policy, then this is where I would claim that in theory, DPO and PPO should be performing equally well. In practice, because supervised learning tends to be easier, converges better, and so on, then you would often see plots like this that suggest that DPO is better, but that's an empirical result. In theory, there's no reason why it should be better. Okay, let me stop here and see if there are any questions as well regarding this. Okay, so then let's continue. Let me now talk about the third diagram here. So the third diagram is another way to improve with respect to reinforcement learning from human feedback. The main thing is that we skip this step here. So you'll notice that you see the two middle steps that are normally the reward model, the fine-tune model. So fine-tuning a large language model tends to be a really expensive step because the language model itself is big, and then fine-tuning it, often you have to leverage various tricks, like using low rank adapters and so on, because there's like way too many parameters to fine-tune. And then even when you do that, you do need to have good compute so that you can fit the model in memory, and then you have to spend quite a bit of time to do the update. So that turns out to be a very expensive step, and that's the step that gets bypassed in this case here. Now, as I explained earlier, there will be a trade-off, which is that now for generation, it will take more time. But we'll see in a moment a technique to try to minimize the overhead at generation time. Okay, so the way this works, it also exploits the same closed form solution that we saw before. So this is again what the optimal policy would look like. So it's the original policy times the exponential of the rewards. And now, since we know this is going to be the optimal policy, we might as well work with that equation directly. So here, if we want to avoid any sort of fine-tuning, you'll notice that what this equation is really saying is that the probability of the next token is really the probability that's provided by the current policy, where we perturb that probability based on the exponential of the reward. Now, it's often good practice for stability reasons to work in the log space. So here we can rewrite this, where I guess this uh, probability of the next token would often be obtained through a softmax. And then here it means that we would work with the logit, so the log of the policy. And here, if we take the log of the exponential goes away, and then we just have the reward. So really, like the way we would sample from the resulting policy is by simply adding to the logits of the language model a reward that corresponds to the reward model that we've learned. So text generation, you see, would simply work as follows. So you could imagine that at inference time, when you want to generate the next token, you've got your original language model. You can use it to obtain a log probability for all the tokens in the dictionary. So that's what this vector shows. And now for each token in the dictionary, we can also get the reward model to tell us what's the reward for each one of those tokens. And then you simply add up these two terms, and then I guess, okay, no, this term here has to be divided by beta. This is a hyperparameter, but otherwise, I mean, you just add them up, and then you pass this through the softmax to obtain your distribution, and that's what you're gonna sample from. Okay, so this is very interesting because you see, it kind of shows how we don't actually have to fine-tune anything, optimize anything. We could just do text generation directly the minute we have a reward model. And then so now there's a series of techniques that exploit that. They're often under the banner of reward guided text generation, because here is the reward on top of the language model that would guide the generation. Okay, so in theory, this is beautiful. We can use that, but in practice, there is one challenge, which is that here you'll notice that in my notation, I'm using a bolded A throughout. The bolded A here indicates that it's an action that corresponds to a sequence of tokens. So this would be like the entire utterance that is produced by the system. So the entire response to the prompt. And in practice, we need to be able to generate tokens one at a time. We're not generating an entire response in one shot. We're simply generate tokens iteratively one at a time. And the problem is that this equation doesn't show us how exactly we could sample one token at a time. This shows how we could, at least in theory, sample an entire sequence in one shot, but there's like way too many sequences because that just blows up exponentially with the length of the sequence. So we need a different way to sample just one token. So here, let me show how we can modify those equations slightly so that we can obtain a token-wise language model and then do token generation based on that. Okay, so the idea is that you see here, if I'm going to generate just one token at a time, I would like to condition the property of the next token based on the prompt, but also the previous token that I've generated so far. Okay, so that would change the equations in this way. So now everything gets conditioned on the previous tokens, and then the reward here, that would remain with respect to the sequence, but now you see it's a partial sequence, right? So in this equation, it was a reward with respect to the prompt S and then the complete response A, whereas here now it's the prompt with a partial response up to token I, right? So now we need a way to obtain a reward model that would allow us to score partial responses. And this is a bit of an issue because um, I, I guess all the techniques that were initially developed for training a reward model, they rely on preference data where there was an annotator that simply ranked complete responses. So two complete responses, then it would indicate which one is preferred. But now asking somebody to look at partial sequences and say which one do you prefer, it's a little bit awkward because we're not sure how that sequence would be completed. And then as a result, it's not clear how to obtain a reward model that works with partial sequences. So this is where, in fact, with my group, we just got a paper accepted at ICML. So you guys are the first to hear about this. I mean, paper acceptance for ICML, the announcement was just made, I think, a couple of weeks ago. And so the conference has not happened yet. So it will be in July. But let me tell you our solution for this. So here we developed a way to train a reward model that can score as well partial sequences in a principled fashion. So our approach can be summarized as follows. So we're going to maximize, again, the log probability of the difference between the reward for the preferred sequence versus the less preferred sequence. But then this will be subject to some constraint, but we would like to make sure that the reward for a partial sequence will be equal to the best reward. So here this max, think of it as like the best reward that can be obtained if I was going to continue this sequence with any possible sequence. So essentially, you can understand that a partial sequence um, should be preferred if there's a way to continue it to obtain a complete sequence that has really good reward. So in other words, might as well pick the completion that will give you the best reward. So that's how we can reason about how to score those partial sequences, because then as the language model generates token by token, it should generate, you see, tokens that gradually construct this partial sequence, always keeping in mind that there should be a way to complete that sequence to obtain a full sequence that is really good, right? So here, that's the idea. That's why we have this max over the possible completion, and now this gives us a way again to score partial sequences. Now to solve this optimization, what we do is we create two loss functions. The first one is the same as before, same as for the Bradley-Terry model, but then we have a second loss function that compares essentially the left-hand side to the right-hand side. Okay, and in fact, you can think of this as a form of temporal difference learning, because you've got here the value for a partial sequence up to token I, and now we're taking a max of the value for the continuation, and here we can just do it like one token at a time. Um, and and yeah, this would correspond to a form of temporal difference learning. Okay, so just by doing this, we can obtain a reward model that also works with partial sequences. So the pseudocode here for training the reward model works as follows. So you simply alternate between the two losses, and then you simply take steps in the action of a gradient, and this works well in practice. Uh, so we applied this and compared it to other techniques that also do reward guided text generation. So in this table, our technique is right here, pharma. Um, we can see the amount of reward that it obtains. It's pretty good. Okay, and then also the amount of time that is required to do inference. So I mentioned earlier that one challenge with reward guided text generation is that there is a trade off. You're going to spend more time at inference time because you have to query the model. You have to essentially um, do this computation at inference time. Whereas normally, if you have a fine tuned language model, then there's no computation per se. You simply call the language model, and then you just get this vector and you sample from that, right? So here we also have to call the reward model, and then so this will effectively increase the overhead, and the amount of overhead would actually depend on the size of the reward model compared to the language model. So the baseline is usually that you use a reward model that's the same size as the language model. So this would then double the amount of time, but very often in practice, reward models don't have to be as large as the language model because they're trained with just a limited amount of preference data. Like the amount of preference data is usually in the thousands, maybe tens or hundreds of thousands, but it doesn't reach millions or billions of sentences like the pre-training that is done for the language model. So you can often obtain very good results with a smaller reward model. And then so as a result, then the overhead doesn't have to be that big. Now in this table here, we compare to DPO and PPO, where in their case, you see the language model has to be trained. So there's a cost here, but then for the inference time, you see it is the fastest, right? So compared to all these techniques that are doing reward guided text generation, it is much faster. Our technique still has some overhead. Here it's a bit more than double the time. That's because we use a reward model that was essentially the same size, but we could reduce that by using a smaller language model. But that shows the overhead. But then you can see in terms of reward, it's on par with DPO PPO roughly, right? And then it actually improves with respect to some of these other methods. Um, Now, when we look at inference time versus win rate, like you would like to have a method that's as good as possible with respect to those two axes, and then pharma is right here. So in fact, you want to have the lowest inference time possible, and then the highest win rate. So the two techniques that would have a better win rate here, um, they yeah, they do correspond to DPO and PPO. Okay, so these techniques can still um, perform better, but on the other hand, you pay a price because you have to spend time training, and depending on your organization's compute, that may not be feasible. So those two here, even though they look better, they're not always feasible. That's a challenge. Okay, so let me stop here again and let's see if there are any questions regarding this material. Okay, so if no questions, let's continue. So now I'm going to talk about the second topic. So reasoning for large language models. This will be a little bit faster. It is actually a very hot topic right now. This is the frontier that we're talking about for large language model. This is what DeepSeek and many other companies are trying to improve. This is where the race is as we speak. And what's interesting is that, again, reinforcement learning plays a very important role in reasoning. Um, Now, just to give you an idea, so reasoning really started to be in the spotlight when OpenAI released a first model called GPT-01 that was dedicated specifically to reasoning. And then after that, there's been many releases by many organizations for all sorts of large language models that also specialize in reasoning. And there's a sense that you see reasoning is really a key capability that can really improve um, the type of responses that a large language model will produce. And now reasoning is needed for math problem, uh, but I mean for all sorts of tasks in daily life, right? If a response is not literally written somewhere, but you need to combine different facts uh, and then infer a conclusion from this, then this is when reasoning becomes essential. Okay, so that's why there's so much emphasis. This graph here stops in March and April, but in any case, it continues, and I expect that there will be again an explosion of large language models that deal with reasoning. Um, okay, in this picture, it's interesting. So this picture, I took it from a survey. It's a very recent survey. It discusses, or at least it categorizes different approaches to enable reasoning. And then in many of those categories of approaches, reinforcement learning happens to be core. So, okay, and the simplest way to think about it is that for reasoning, so you have an input to the large language model. The large language model itself, we can think of it as a reasoner. So it will produce some steps with an answer, and then often it might aggregate some of those possible reasoning steps and then provide a final answer. Okay, so we're going to see in a moment how that can be accomplished. Like normally, a large language model will simply produce a sequence of tokens, and that's it. But now, if you ask it to respond to a query that is complex because it requires reasoning, it might produce several responses and then combine them through some form of aggregation to produce a final answer. So this is one way to achieve reasoning with just a standalone LLM. Now, something that's a bit more elaborate is to um, have the agent essentially, so this is our LLM, okay, it might um, start producing some steps for the answer and then get some feedback from the environment. And here what we mean by the environment, depending on the task, like if it's a coding task, there might be a compiler that would indicate whether this code could even run. There could be a knowledge base that will verify that maybe some of the facts that it's reasoning with are correct and they're not hallucinated. Or more generally, there could be a verifier. So this is like anything that you could use externally to the LLM to provide feedback about the steps that it's producing so far. And now you see, it doesn't have to be just one generation of tokens and then done. So it could be an iterative loop. And I mean, this is essentially the reinforcement learning loop, right? Where you produce some action, you get some feedback, then you produce the next action, get some feedback again, and so on, right? So basically, reasoning for LLMs is naturally modeled as a form of reinforcement learning. Now, this picture assumes that we just have a single LLM. It's doing the reasoning by itself, just interacting with some external tools, in other words, the environment. But we could also imagine that for some complex tasks, you could have many LLMs, so many agents, and then together they're trying to construct the answer. And you can think of this as like whenever a patient goes to see a doctor, and then perhaps the patient has some complex health issues, and now you need a team of doctors that have different expertise that will essentially um, express their opinion and contribute to the diagnosis, and eventually there's a final diagnosis that is provided, right? So in the same way here, for some tasks, often you would need to have different LLMs that provide different perspectives, or they may essentially decompose the task into different steps, and then they're carried out by different agents, different LLMs. And now there's some really interesting questions for communication and coordination. And really this now becomes a multi-agent reinforcement learning problem. Okay, so this is the frontier, and what's interesting is a lot of people in NLP would essentially talk about these single multi-agent aspects, but if they're not experts in reinforcement learning, they may not necessarily leverage the best techniques from reinforcement learning for this. So there's actually a big opportunity to have some important contributions here. Okay, now let me go into more details about some of the techniques that do use some form of reinforcement learning. So if we have a single agent and it's going to do some reasoning, one of the early approach that was very popular is to do chain of thought reasoning. So chain of thought reasoning, the idea is that you have the question and then you have some steps where the question, you would also provide a prompt where you would tell the agent, let's reason this step by step. And then the agent will essentially respond by saying, okay, my first step is this, my second step is that, etc. And then my conclusion is this, right? And then just by verbalizing these steps, it tends to produce final answers that are better than if you ask it to just provide the answer directly. Okay, so chain of thought really kicked off, I mean, this whole endeavor to do reasoning, and it was amazing. Now, chain of thought, you would produce just one sequence of steps and then arrive at the answer. But when you work with large language model, because they're trained to be policies that are stochastic, you can essentially ask the same question multiple times, and then you're going to get different answers. And in this case here, if these answers include steps, you might get different steps with a final answer that might be different in each case. So now an interesting question is, what do you do if each time you query the LM, you get something different? Well, what you could do is in fact leverage this and then think of that as like many trials, so many possible hypotheses for what the answer could be. And then either the LM itself or otherwise something external could rank those answers after that, and then perhaps pick the one that it thinks is best, and as a result, improve further what the reasoning is like. So here, best of n simply stands for the idea that we simply ask the LLM to provide n responses with their steps, and then we rank them, either the LLM again itself doing that or something external. Now, we don't have to stick to just sequences. We could actually produce, actually, no, sorry. When we produce sequences, we don't have to produce entire sequences in isolation. We could start by producing some response and then eventually realize that, well, this is not a great direction, and then backtrack and so on. So this would correspond to a form of tree search. And then, at least in NLP, one form of search that is popular for decades is what is known as beam search, where you always generate multiple responses in parallel, and then at every step you increase the number of directions, but then you prune this back by essentially just retaining the best one. So like you can see here, we would provide responses, and then what's in red means that this was pruned. So far that response was not good, so we just dropped it. Then we continued with these two branches, and then we pruned some more after that. So the idea is that as long as you have something that can score or provide feedback to partial responses, then beam search will work well in that respect. Okay. So now let me go back to tree search. So here, perhaps, I'm assuming in the course you guys would have seen Monte Carlo tree search. So Monte Carlo tree search can be applied directly here to do reasoning. And just as a brief recap, the way Monte Carlo tree search works is that we're trying to find the best policy at inference time, and this is done by expanding different branches, but we do this in a smart way, right? So first we would select a branch, expand it by one more node. So that's what we see here. And now to evaluate this branch, we need to have a value for that last node. So we could use a default policy to do a rollout, get a reward, and then propagate this back, right? So that's how Monte Carlo tree search works. And then you repeat this again. And this way you gradually create a tree, but it's not a tree that examines everything. It's just smart in terms of always expanding what seems to be a promising branch each time, so that you can focus on the branches that really could lead to the best outcome. Yeah, so Monte Carlo tree search applies directly here, and then there's several papers that have used that to perform reasoning with LLMs. Okay, another approach, instead of doing the reasoning at inference time, why don't we train the model to reason? Okay, so that at inference time, we don't have to spend a lot of time, because the challenge with these approaches here is that now the inference time will be longer. So in fact, if you've played with some of the reasoning model, very often their response will not be immediate. They will take some time to respond. And the reason is because they have to do extra computation. They're not just generating one sequence. They might be generating n sequences or an entire tree or several branches like that, right? And that increases the time. So if we want to avoid increasing the time, then we have to go back to the idea of training. And so there's a whole line of work that looks at learning to reason, and it can be thought in this way. So here, perhaps we have our policy model. It can generate some output, and then we can evaluate it either by comparing to a reference output or assigning a reward, assigning some value, and then we can modify in that way our output and iterate, okay? So to do this, if we're going to use reward, let's say, there are two common regimes for the reward. One of them is known as the process reward model. So the idea is that the reasoning steps, perhaps we can have some external tool that will tell us each step whether or not it's a good step by assigning a reward. But this is not always possible, so obtaining rewards at every step either requires a human annotator or otherwise some automated way. So in the case of coding, that might be possible because you can simply use, let's say, the compiler to tell you whether, I guess, the code so far would compile or not. So if you have automated ways like this, then this is great, and you can obtain a reward for every step of your reasoning until you get the answer. But otherwise, what is perhaps more convenient is to use what is known as an outcome reward model. So for instance, in math, you might have a problem where there's a description of a mathematical problem, and then let's say somebody knows what the answer, and then can essentially write a simple function that would compare the answer of the LM to the correct answer. So then it would be a reward that could be assigned just based on the final answer. So the steps are not being scored, but then the assumption is that if you're going to arrive at the correct answer, hopefully that's because you carried out steps that make sense. I mean, it's always possible here that some of those steps might be erroneous, but usually the idea is that there's a high correlation between having the right answer and having correct steps along the way. Okay. So in any case, this is where reinforcement learning can be used to fine-tune the large language model. And in fact, for this, there was some work done by the team at DeepSeek where you can use the PPO algorithm, or in their case, they in fact came up with a simplified version of PPO that they call GRPO. So GRPO stands for Group Relative Policy Optimization, and we can see the differences between those two. So you see, we saw earlier how to use PPO for preference alignment, but in reality, the preferences are used to learn a reward model, and then after that, you're really just doing reinforcement learning with the reward model. In the case of reasoning, the idea is that you don't have to learn a reward model from preferences, but you would use external tools to essentially verify whether the answer to a math problem or the answer to a complex query is the right one, and then so that then you have a reward model. So it could be you see an outcome reward model like this that just provides a reward at the end, or it could be a process reward model that gives you rewards at every step. So either way, then you can fine-tune by reinforcement learning. You can do this using the PPO algorithm, or you can use this improved version that DeepSeek developed in 2024. It's an improved version in the sense that it bypasses the need for a value model that would normally be used in the computation of the advantage function. So here, in PPO, you see PPO is an actor critique algorithm. So it has a policy that's the actor. It has a value model, which is the critique. So you have those two pieces. And you can imagine that for large language models, the actor, this is the LLM, it's big. And now the value model usually is roughly the same size as the policy because, I mean, it doesn't output an action, but it outputs the value that an action would correspond to. So, it needs to be on the same size, about roughly the same size as the policy. So now it means that this algorithm is really working with two large models, one for the policy, one for the value model. And then the improvement in GRPO is that we essentially get rid of the value model. So here the idea is that we needed the value model in PPO to essentially produce the advantage function, because normally you take your sum of rewards and you subtract from this the value obtained by the value model. But the question becomes, is it possible to subtract a baseline that could be obtained more cheaply without having a second large model? And the answer here is that we can simply use our current policy to produce many trajectories, take the average of those trajectories, so the average sum of rewards of those trajectories, and treat this as our baseline. So here it saves a lot in terms of memory. So in fact, with large language models, this is often a big issue because they're so large that you cannot afford to have many models that are of that size. So if you just have one, that's great. Now you have to spend a bit more time because you're generating many sequences to obtain an average reward based on that policy, but it saves you in terms of memory. So that's the main idea. And now, in terms of pseudocode, how does this group relative policy optimization technique work? Well, it's very, very similar to PPO. So you see you have the same kind of update that we would do here for the policy. The main difference is how we compute the advantage function here. And the advantage function, again, is the sum of the rewards minus the mean of those rewards when we have many trajectories divided by the standard deviation. So essentially, simply normalize here, and this is our baseline effectively. Okay, so that's how this works, and yeah, it helps with scalability. So when the team at DeepSeek released DeepSeek R1, so this was a model that has some reasoning capability, they compared it to some of the other state-of-the-art models from OpenAI, and you can see that on various data sets, so various benchmarks, it does perform really well. Okay, so this is the accuracy. So you see the first column, dark blue, is DeepSeek R1, and then yeah, it's on par with OpenAI O1. So this was remarkable, and DeepSeek R1 is open source, and they have a tech report, so it's really nice to see how it was obtained. And essentially, it was obtained by doing reinforcement learning with GRPO. And then the beauty as well that they highlight in their paper is that there was no supervised fine-tuning here. So normally you see the steps that I described at the beginning, the recipe for training large language models, that you first do supervised fine-tuning, then after that you do your reinforcement learning, and here they skip that step. So it was reinforcement learning only that allowed these reasoning capabilities to be mastered by the agent. Okay, so perhaps one more topic that I want to mention is known as reflection, or if you prefer, verbalized reinforcement learning. So I explained how agents now, when they do their reasoning, they could get some feedback from the environment or from something else. And in fact, the simplest is, if you don't have anything in the environment that can provide some feedback, can you use the LLM itself to essentially critique itself? And that turns out to be something worthwhile doing, and you can improve the results. It's just like, you see, when you write some text, and then after it's written, you just read it again by yourself, then you would often notice all sorts of issues and then improve the text, right? And then you might do this several times and then obtain something that is much better. So in the same way here, you can get an agent to produce steps for a reasoning task, and then ask the agent, after it has produced those steps, look at the steps you produce yourself and critique yourself. You know, do you think those steps are good, or do you think anything should be adjusted? And so you can get this type of critiquing or reflection style loop. And the idea is that then um, we yeah, we obtain something that is better. And I've got here on the right hand side a I guess some examples in the context of decision making, programming, and reasoning for using reflection. And the key step is this step here, where the agent essentially looks at its own answer and then will provide comments that are essentially feedback to itself. And then the next step after that is to use those comments and try to come up with an improved answer. And then yeah, on various benchmarks, you can see that doing this, and here the x-axis is the number of trials. In other words, the number of steps where it critiques itself and tries again. Then as that increases, you can see that it can further improve with respect to just doing chain of thought only. So yeah, so this is beautiful, and now this is being used for all sorts of tasks and all sorts of scenarios. Okay, so let me conclude now. So I talked about how reinforcement learning is key for large language model alignment and also reasoning. And what is the current frontier for anybody who's interested in, like, you know, contributing and perhaps advancing the state of the art? I realize this is a course, but if anybody is into research, then I would say the current frontier is in fact multi-agent reinforcement learning for agentic orchestration. So what that means is that you have a team of agents. They are working together on a task. They are performing different steps, or otherwise performing or providing answers for the same task, but then these things need to be aggregated in some fashion. And now there's all sorts of questions about how we're going to coordinate those agents, and then how we're going to decide when different agents provide answers that are conflicting, and so on. So what's the negotiation and all that. So this is a frontier. So companies are embracing now multi-agent systems for workflow automation. Most of it is designed by hand, but when you design things by hand, they're never perfect. And over time, different steps in the workflow might change, which might lead to a breakdown. So there's a need to automate how you're going to, I guess, optimize the entire ecosystem. And multi-agent reinforcement learning is perfect in that respect. Okay, so I'll stop here. So this is it, and thank you, everyone.
Thank you, Professor, for your great talk. Just I know our time is up, but if you have a few minutes, just see if anyone has questions.
Sure.
Okay.
Hi, can you hear me?
Yes, yes, I can hear you.
Hi, Professor Poupart. I'm follow your working in reinforcement learning, and thank you for joining this conversation. Uh, uh, Thank you for your informative and helpful presentation. My question is, in the context of aligning a large language model with human preferences, how do you compare the trade-off between stability and scalability of three methods that you mentioned, DPO and RTGT and PPO? Please answer this question, and I have another questions. And compare these methods with your proposed methods in terms of stability and scalability. Thank you.
Okay, great. Yeah. So uh, perhaps part of the answer is what's in those three bubbles here. So for scalability, this one tends to be the most expensive, therefore the least scalable for training. Okay. This one is more scalable because training tends to be cheaper, um, and also more stable. So maximum likelihood tends to be easier to do optimization than reinforcement learning. It's also cheaper, and then we avoid that step. So this is clearly less expensive, and then there's less instability. Now, the most inexpensive training is here, because now we, in fact, bypass completely training. So there's no training, right? So this is the most inexpensive, the most scalable with respect to training. But then there's a trade-off with respect to generation. You see the other two, generation is very simple. You just sample directly from the fine-tuned language model. Here we have to do some computation at inference time that involves querying the reward model. So as a result, generation is going to be slower. So that's the trade-off. Okay. And now for my technique, it is within this family here. And I guess I'll just show again the results so we can show, we can see um, in terms of like inference time, right? So I did mention that there's a cost, and we can see these techniques do take more time to generate answers. So here, this is the amount of time in minutes for generating 100 answers to 100 questions on average. Okay. And compared to DPO and PPO, which were the other two techniques,
Yeah.
right? These have fast generation. So that's the trade-off that we observe here. But you can see here there is no training. The LM is frozen. Now here we have to train the LM, and depending on the organization, this may not be feasible, because if you don't have the compute to do that, then you're simply stuck, and then this becomes the only option really.
Yeah. Let me ask one question, if I can. Uh,
Yeah.
what alternative source or mechanism can be used to define effective reward signals or training large language models (LLMs) via reinforcement learning without relying on explicit human feedback or preference data? Without relying on explicit human feedback, uh, um, without RLHF, can RL only use these techniques and improve our works?
Right. Okay, so let me go to this picture here. So okay, in this picture, what it shows is that we can get feedback in the form of rewards via automated techniques in some situations, where if we're doing code generation, the compiler can provide the feedback. If it's a form of information retrieval, or we're looking at different facts and then you can uh, verify this in a knowledge base, then that works. And then sometimes you can get another LLM to act as the critique, and then provide the reward, and this one may or may not need to be trained. Okay. So in fact, I am at the moment doing some work with one company, and what we did is we got some amount of human feedback, then we trained an LLM to serve as the critique, and in other words, a reward model, and then it was able to now we're using it to do reinforcement learning from human feedback in this fashion, and it's working fine. So I know that when we talk about preference data, it might seem like, wow, I'm gonna, how am I gonna get that preference data? This is a burden for humans, but often you can get by with like hundreds to thousands of examples. And at least with the company we're working with, in their case, doing hundreds of examples, they have labelers, and they do this within a couple of days. So it's not, you know, uh, impossible, but then it really improves the performance, because then you have data specific to the task. So that's the key. So yeah, so it remains a bottleneck, but it's really helpful.
Yeah, possible for industry, but not for academy. Yeah, right.
Well, so I mean, in this case, um, like for academia, I mean, with my students, we also do some labeling, um, and we would do also on the order of hundreds of label point. The example I gave, I mean, the company is developing a product, so they want to get their domain experts to do the labeling. I cannot, like I'm not using my students to do that, simply because they're not the domain experts, and the company would not value their labeling in the same way as their own experts. But otherwise, we could have done it ourselves, right? So when I talk about hundreds of examples, that can be done in a matter of days, and that's just fine.
Thank you so much, Professor Puba.
Okay.
Thank you, Professor. Just if you have time, just for the closing question, I want to ask you what is your advice for the students who are just starting their research journey and want to tackle something interesting? What do you suggest them? What courses to take on? What they're gonna major on, or what projects work on? What is your advice for them?
Yeah, great question. So I think there's in fact a lot where reinforcement learning can contribute in addition to what has already been done for large language models. And as I was explaining in my conclusion slide, let's just go there. Um, yeah, I do think that it's for agentic orchestration that right now this is completely open. Um, there's plenty that can be done. Maybe the challenge is that this would often involve multi-agent RL, and if you're just starting, you might want to just consider single agent RL. So for single agent RL, when I discuss here verbalized reinforcement learning, this is still a very recent topic. This is, I think, fascinating. So normally for reinforcement learning, we get rewards that are numerical. In verbalized reinforcement learning, you do not have numerical rewards, but you have verbal feedback. And the techniques here, in fact, do look quite different than the traditional techniques that are based on policy search or Q learning and so on, because they would all leverage numerical feedback. But now this is essentially like a new open field. Like if you have feedback that is not numerical, how do you use it? And this is one line of work that explores ways of doing that. And I would say this is very simple. It's not complicated at all. And if somebody, in fact, does not know much about the traditional techniques of reinforcement learning, then you're not at a disadvantage, because here, if you don't have numerical rewards, you cannot use anyway the traditional method. So you're probably better off, because then you can just think with an open mind, as opposed to always thinking how you can reduce the problem to an existing approach. Okay, so this could be a very good direction for people who are just starting.
Okay, thank you, Professor. I think it was a great answer, and thank you again for your great presentation and accepting our invitation and spending your morning with us.
Okay,
Thank you.
perfect.
It was
Thank
truly an
you.
honor. Okay, thank you, and I think we are very out of time. Okay, and thank you, and have a good rest of the day, dear Professor.
Okay, all right. Bye bye.
Bye.